Hello all, so let's continue with our solved problem on conditional probability. So in last lecture we saw the basic introduction to conditional probability, and now we will see some examples and then move to Bayes theorem, which is one of the fundamental ideas in conditional probability, and this will be extensively used in many machine learning problems. So here the question says that bin has 25 defective so let me just highlight side by side that there is one bin and there are 25 defective transistors. So defective, it means that will fail immediately when they are put into use. Then 10 partially defective, so that fails after some couple of hours, you can say. And 25 acceptable transistors, so which are perfectly in a perfect condition and they won't fail. So now the question is, a transistor is chosen at random and from and put into use. Okay, so from the bin end, maybe this is yeah, so this is end, put into use. So if it doesn't fail immediately, so the condition already which is satisfied is that if it doesn't fail immediately, so it means that they are not from, sorry, here it's 5 only, not 25, my bad. So they are not from this 5 defective transistors. So if it doesn't immediately fail, then what is the probability that it is acceptable? So we can just directly do this problem, because the sample space is being reduced after this condition that it doesn't fail immediately. So they are not from this 5 effective transistor. So they are from this two categories. And our question asks, what is the probability that this is acceptable? So our sample space is reduced sample space because of this conditional thing, is that in total we have 35 transistors. So let me just write required probability is equals to, in total we have 35 now, in our reduced sample space in total we have 40, but since we already know the condition that this is excluded because it doesn't fail immediately, so these two are the cases. And the question asks, what is probability that it is acceptable? So how many acceptables are there? 25. So we can just directly write 25 by 35, which is 5 by 7. So this is a really simple way of like thinking in the any probability question, especially the conditional probability, that our sample spacing being reduced. But what if we want to solve like a traditional problem, like an extensive way? So I'll do the same now. So we are asked that we have to find the probability that it is acceptable, provided it doesn't fail immediately. So when it doesn't fail immediately, so they are not from this category, which I already said. So they are not defective, right? Can we write like this, that they are not defective? So using the formula that we just derived in the last lecture, this will be intersection of this two. That is, it should be acceptable at a time intersection with not defective. And in the denominator it will be probability of not defective. Now here we are we haven't reduced our sample space, we are doing a traditional way. So this is a simple thing, using reduced sample space. But here our sample space will be all consist of all 40 transistors that we have, that is 25, 10 and 5, that is in total 40. So let's calculate numerator first. Let me change the color. And in the numerator it shows that it should be acceptable as well as not defective at the same time. And we know that these two categories, that is 25 and 10, these two categories are not defective. But how many acceptables are there? 25, right? So in total we have 25 acceptable out of how many? 40, right? Or let me put it the other way, if you didn't get this, that these two conditions needs to be satisfied at a time, and this will be satisfied only when this is acceptable. So probability of acceptable along with non-defective is equal to probability of acceptable only, and still we are having the same denominator. What is the probability of non-defective? So let me just put this away for a while. So I hope this point is clear that it is a probability of acceptable. So transistor will be both acceptable as well as not defective only when it is acceptable, right? So we have to write the probability of acceptable now, and acceptable is really clear, like it's 25 acceptables out of 40. Here it should be 40. This is really important, that we are not reducing our sample space like we did in this like direct solution that we did for by using the reduced sample space of what 35, right? So the numerator is clear now. Now same thing for the denominator, that we have to find probability of non-defective, and we know that how many non-defective are there, 25 and 10 is 35. So out of 40 there are 35. So this 40 cancels, and at the end we get 25 by 35, which we got in our this direct solution using reduced sample space, which is 5 by 7. So these are the two ways that you can calculate conditional probabilities in this question. So I'll request to go through the rigorous method, that is this one, long method, and then think of this afterwards. Now let's move towards next topic, which is, now let's recall again that this is what we derived in our last class, that if we have two events E and F are two events, then probability that of occurrence of event E given F has already occurred is intersection of both. This is intersection. I'm not writing the intersection symbol in between, but you can write if you want to, and divide by P of F. So can we write just, if we want just E intersection F, that is the occurrence of both the events together, if we want this probability, then we can just simply rearrange and make this as our subject, and we just simply get E intersection E given F, sorry, and into P of F. Can we write like this? Simple mathematics. So this formula will be helpful. What it says? It says is that the joint occurrence can also be calculated using conditional probability and the probability itself. So E given F has already occurred, that probability and multiplied with probability of F will give the joint occurrence. And this will be useful in many problems where we have to calculate the joint occurrence of the probability. So let's take an example for that. So let's say there is some Miss X, and figures out that there is 30% chance that her company will set up branch in NYC. So it's in New York City. So there are 30% chance that some Miss X, I don't know, like it's an anonymous name. So 30% chance that company will set up branch in NYC, and if it does, then she is 60% certain that she will be a manager. She will be made a manager for the new operation or the new position. So what is the probability that this Miss X will be a NYC branch officer? So now two events are occurring together. That is, firstly, the company is set up in NYC, as well as Miss X is a branch office manager over there. It's appointed like that. So our task is to calculate both of them. So firstly, let's say we have two events again. So probability that E into F, E intersection F, I mean. So what is E? E is that, let me write with new color. E is that chance, or we can say event, that company set up branch in New York. And F is the event that she will be a manager over there. She will be appointed as a manager, will be good. Appointed as manager over there. So just what we have seen in our previous slide, that we can just simply write like this: E intersection F into P of F. So we'll just write P of E intersection F into P of F. Now what is this event? P of E intersection F. P of E intersection F will be the event that the company what is the probability that company will set up branch in New York given that she will be appointed as a manager. So this will be, because it's already given that if it does, that if company opens the branch in New York, then there are 60% chance. So this probability, this conditional probability is given as 0. 0.6 to us. 60% means 0. 0.6 in terms of probability. And what is P of F? P of F will be that she will be appointed as a manager, right? So what we can write, we want probability of F, which is she will be appointed as a manager. So are we given with that probability that she will be appointed as a manager? We are given that 60% is a chance. Okay, so here we don't have this probability in our question, but can we do something like this, that can we just interchange E and F here, that F E into P of E, because we already know P of E. What is our E? E is that company will set up branch in New York, right? This we already know, which is 0.3. And this is now what? F, which is she will be appointed as a manager. What is the probability for that? Provided that company already set up the branch. So company already set up the branch and she will be appointed as a manager. That probability is 0.6. So here we have both of these probabilities, and this is what Bayes theorem says, that this two should be equal at the end. And this is our Bayes formula that we will derive in our very next lecture in a rigorous way. So don't worry about that. So we can simply write multiplication of this two, which is our required joint probability, will be of course 0.18. So I hope things are clear. Like, you thought of this first, then you saw that P of F, we don't have that. Or maybe I did a mistake here, that P of F, what was F? F was that she will be appointed as a manager. So okay, so here we don't have to take this much, because this means, it doesn't mean it's 0.6, because what we denoted F as she will be appointed as a manager is already occurred. That is the condition, that is, or the event that has already occurred. But here the condition which has already occurred is if it does, that is, if company set up a branch in US. So E is the event which has already occurred. So that's why this formula was useful here, right? And not this one. So I hope things are clear, and we will see each other in next lecture, in which we will derive the Bayes theorem. So you already saw this, how Bayes theorem works. So you have to be adaptive based on what is asked and what is given in the question. Right, so stay tuned. I hope the lecture is useful to you, and see you in the Bayes theorem lecture. Thank you.